Okay, these marks are just for me, so I can know what you can see on the screen, so I don't write over the edges. Okay, oh, I don't have much space. Let's see how we go. We're going to start by talking about the SN2 mechanism. Okay, so this is the mechanism when we have a primary haloalkane, and I'm just going to use X for the halogen. This could be chlorine, it could be bromine, it could be fluorine, it could be iodine. Okay, and I'm going to just use these groups. Okay, I know this is a primary haloalkane because the carbon that's bonded to the halogen is only bonded to one other carbon. Okay, so what happens is the nucleophile comes along, and that nucleophile, it could be the hydroxide, it could be the ammonia, it could be the cyanide. So I'm going to choose hydroxide. Okay, with my lone pair of electrons, it has a negative charge, and that is going to attack the carbon here. Now the reason why it attacks that carbon is because there is a partial charge across this bond. Okay, this bond is a polar bond because the halogen is more electronegative, meaning the electrons are positioned more towards that halogen. Okay, giving this one a partial negative charge. There's a little mistake there. Okay, what happens then is this goes through a transition state, and in that transition state we have, let's pop these groups back in. We have the process where this bond is breaking, so I'm just showing that as a dotted line, at the same time that this bond is being made. Okay, because it's a transition state, we're going to show this in square brackets with a little sign here to show that it's a transition state. Okay, now we do need to put some charges in here. This one is going to be partially negative, as is this one. Okay, because this is where the electrons are, leaving that carbon still as partially positive. Okay, so overall we can say that this transition state now is negatively charged. Okay, this transition state cannot be isolated, so I can't stop the reaction here. It's simply a phase in which the reaction goes through. Okay, I'm going to pop an arrow onto this bit just to show that that bond there is breaking. Okay, notice how we're using double-headed arrows because that shows the movement of two electrons in that covalent bond. Okay, now I am just going to have to rub this out because I'm running out of room on the board, so just bear with me a second. Quickly redraw out this transition state again. Oh, I should stick with, I'll stick with the groups that I had before. Okay, so what's going to happen now is that this bond completely breaks. So the leaving group, the halogen, is going to break off, leaving us with our new product. Now, what we have here is something called an inversion of configuration. And what it means is that because the nucleophile is attacked from the left-hand side, these groups then get pushed over to the right-hand side. Okay, so where they were once lying over this side, they're now lying over on the other side, and we call that an inversion of configuration. And it's just like when you have an umbrella on a windy day and it gets turned inside out. Okay, so let me just show you how that looks now. Okay, so you can see simply from the product at the beginning, the groups have now been pushed over to one side. Okay. Also, what we also must remember to show is that leaving group as one of the other products of this reaction. Okay, a couple of key terms then which I can talk about here is this breaking of this bond. We can call this heterolytic fission. Fission just meaning breaking, and heterolytic meaning that both electrons in that covalent bond are going to one side. Okay, so we're not homolytic like we have with the radicals, heterolytic to show both electrons going to one side. Okay, we can also call this a stereospecific attack. Stereospecific is all about the shape of the molecule and any bulky groups that are in there. Now, what you saw is that the nucleophile attacked from the left-hand side. So therefore it is stereospecific. Okay, the nucleophile is not going to come on the same side as the leaving group. It's going to come on the opposite side of the leaving group. So therefore it's going to determine the shape of your final product. Okay. And the other term that we can talk about is this one that says little steric hindrance. Okay, steric hindrance is all about bulky groups that are getting in the way. Okay, now what you can see here is that we have two tiny groups, the smallest atoms that we can. So there's next to no steric hindrance here, and then just one relatively small group there. So these groups don't get in the way of that nucleophile. So the nucleophile has lots of space to come and attack that carbon there. Okay. All right. I'm going to stop that there, and then I'll go again with SN1.